So today's the tutorial 7. And in this tutorial, there are 2 parts. The first part is how to modify the GUI using Glade and GTK. And the second part is how to profile and measure where time goes in your program. I'll start with the first part, modifying the graphical user interface. So remember from the last tutorial, we were opening the main window from this file, libstreetmap resources main.ui. And in this tutorial, we are going to modify this file using Glade. If you open this file in Glade, it is a GUI editor tool that allows you to rename components, move positions, add new components like text boxes, like overlays, and useful stuff like that. So our first demo, to start with something simple, we'll open the main.ui file inside Glade. We'll change the window title to something that's not default. We'll use the Glade packing to move our menu bar from right sidebar to a left sidebar. So I'll go to the same demo folder as what we saw last week. And just to show what it has right now. So currently it's only drawing all of the intersections, and it has the select intersection feature implemented correctly. Its title is called EasyGL application example. That's the default title. You can zoom in, zoom out, zoom fit, and pan using the buttons on the right. The intersection selected is displayed at the bottom in the status bar. Now let's open the libstreetmap resources main.ui. We'll see that this is the main window. If we click on it and preview, this is the default window layout that you will see. On the left, we have the hierarchy of the different components starting from the main window. Inside main window, we have the outer grid, which is everything here with 3 rows, 3 columns. And we're only using 2 rows, 2 columns. Inside outer grid, we have the main canvas area, which is here. The inner grid, which has all of our buttons. And that's the right sidebar. We can see inside general, its ID is called inner grid. It has 7 rows, 1, 2, 3, 4, 5, 6, 7. It has 3 columns for the 3 pan buttons. And inside packing, it has the current coordinate in terms of the outer grid, which is 1, 0. The main canvas is at 0, 0. And if we move down, you see the up button. Inside packing, it has the coordinate system with respect to the inner grid, and this is at 1, 0. The down button is at 1, 2. Left is at 0, 1. So 0, 0 is at the top left. and it moves down. All of the zoom buttons have width of 3 to span all 3 columns on each row. Then at the end, we have the status bar that has width 2 to span the entire bottom area. And its coordinate is at 0, 1. So our first thing we want to do is to change the window title. So we go to the main window. Under General, see we have the ID. This is the same string that we will be referring to inside our code. To change the title, it's down here. EasyGL application example. We have to first ensure that this checkbox is unchecked. And now we can change this to something like ECE297 demo. Now, if we click preview, we see that this already is showing here, ECE297 demo. And I'll save this. I'll go to the terminal. I'll make this run in the background, and I'll run mapper again. Note in this case, we don't have to recompile because we only changed this file that the EasyGL is reading from, and the title is already changed. Now I'll go back here and I'll move the sidebar from right to the left. And how to do that is I go to the inner grid, which is the sidebar, go into packing, and I change the respective coordinate to 0, 0. See that this is moved to the left. Then I'll go to main canvas, and I have to remember to make it 1, 0. So I moved the main canvas to the right. If we preview, we can see that the sidebar is moved to the left. I'll save. And I'll run mapper again. And we see that the change is already showing here. I'll change them back now. And continue on to our next demo. For the next demo, I would like to add some widgets with Glade. And in this demo, I will only be adding a text box to the sidebar for text entry. And what it will do is I have a separate button called Pinkify that toggles Pinkify every time you click on it. And it also gets the text and display it on the status bar. Let's see how to do this. So the first thing we want to do is we want to add a new widget inside Glade. In this case, in the last week's tutorial, we showed how to add a button to the sidebar without modifying main.ui in Glade. That's one option. And the other option is directly adding it inside Glade. So I will need to add one more row in inner grid. So I'll increment this to 8. I want to keep the proceed at the bottom. So I'll go inside here, go to the proceed button. I'll go to the packing and change the top attachment one down. Now I want to add a text entry. Text entries are in control GTK entry. That's a text box. And if you want to see what it does with GTK entry selected, here is the documentation button. If we click on it, it has all of the documentations for GTK entry. It's a single line text entry field. Here are all the functions. You can get the text entry entered in the text box using this function, for example, and it has many more. Here are the properties that some are very helpful if you want to do something like password or search bar or anything like that. There are the style properties for styling. The signals, I'll cover that later. Types and values. Object hierarchy. We see that GTK entry has two children that might also be helpful if you want to look into them. And here are the inheritance tree. Detailed description, and then the functions. So in this case, I want to first adjust how it looks like. I wanted to span the two columns, so I'll add the width by 1. I need to assign it an ID so I can refer to it in the code. And the ID I'll be given to this one is text entry. This is the exact string you should be referring to inside the code. And I'll keep everything else at default. For usability, I want to have something on it to describe what it does. So I'll go to display and add a GTK label at the empty row on the left. For this one, we have to assign an ID to everything. So I'll give this to my text label. And I'll change the text to pink text. So this text will be shown every time we click on Pinkify. We're not adding the Pinkify button inside here. We will be adding that inside our code. By preview, it looks like this. We have the label, we have the text bar here, text entry. For aesthetics, you might want to do something else to make sure that these 3 columns are balanced, but I'll not be doing that in here. I'll save this. I'll go into our code and I'll select the draw map with Pinkify button. So it's here. Everything else are the same as what we showed the last week. Inside the initial setup callback function, we are adding in a Pinkify button on the 6th row. So this is the row where the text box is at right now. And when we run the program, EasyGL will push the text box 1 down and insert the Pinkify button there. Its callback function is toggle pink with text. And in addition to just toggling the Pinkify flag, we are getting the object text entry. This is the ID of the text entry, GTK entry object. It returns a G object pointer. And if we look at the documentation, G object is the base object for all of the widgets inherited. And now we know that the GTK object is a text entry, GTK entry object. So we can safely cast it into a GTK entry pointer. With this GTK entry pointer, we can then make use of all of the functions here. And in this case, we are using the GTK entry get text, which is called like this: GTK entry get text, GTK entry pointer entry. So we're using GTK entry get text, GTK entry, and it gets the text in string format. So in this case, it's a character array. We'll send the text directly into update message, so it shows up in the status bar. And we'll do a force redraw. See what it does. This is regular release mode compile and running. See that the Pinkify button is here. This Pinkify button is added entirely inside our code. This pink text is added entirely in the glade. And in our text, we are referring to it and getting whatever is entered into it. So if we enter something, nothing happens until you hit Pinkify, and test will show up here. And that's one option of linking our widgets we added inside Glade to our code. If we look inside Glade, we can see that there are two other tabs, common and signals. We are not using them for now because we are writing our code inside. We're writing our code and we're linking inside our code. These two tabs can help you by Glade generating code for you. If you want to use that, we're not going to show you how to do that, but everything should be inside the documentations. Okay. That's demo 12. So after demo 12, you should be getting something like this. In here, it's not swapping proceed and with the pink text, but everything else is the same. Adding the GTK entry widget, you will need to add in Glade using the packing tab to adjust position accordingly. And inside our code, we're using GTK entry get text in a callback to get the text. So in this case, the callback is registered with another widget, which is the Pinkify button. In our next demo, demo 13, we're going to add overlays and register callbacks directly with our widgets. GTK overlay is used to stack UI elements together, and this is useful if you want to display stuff on top of your canvas. And we'll be registering the callbacks directly with GTK using gsignal connect. So how to add a GTK overlay on top of the main canvas? The first thing we want to do is we want to get the main canvas out of your way by dragging it onto one of the empty grids. I'll drag it here. And I'll go to containers and add a GTK overlay. I click on where you want the main canvas to be. And now there is the GTK overlay. And I will be giving this ID main canvas overlay. Now I'll go to main canvas. I'll cut and go to the main canvas overlay, paste. So under main canvas overlay, I have the main canvas now. Previously, main canvas was on the layer that's at the same layer as the main canvas overlay, and now I'm adding the overlay and I'm adding the main canvas under it so that I can add more components on the main canvas. Now, the second thing we want to add is if we want to add some widgets on top of the main canvas, I'll add another GTK grid on top that is 3 by 3. I selected the GTK grid and I click on the main canvas overlay, right click and add widget here. So we added the GTK grid below the main canvas. And if we see it actually running, it's above the main canvas. And I will call it main canvas grid. I'll keep the rows and columns to be 3 by 3. If you want to add more to it, you may do that. And inside packing, we see that the index is set to 0 because it's not the bottommost layer. And I will set the pass-through to on. We have to set pass-through to on so that our mouse clicks are still passed on to the main canvas. That is the grid that we can be adding stuff on to. And now I just want to add I'll just show how to add something onto it. I'll add a GTK switch so it's under control. I'll add a GTK switch that replaces the pinkified button before. So if you turn on the GTK grid, the switch, it's pinkified. If you turn it off, it's not. So I'll add it here at the 0, 0 position of our 3 by 3 GTK grid. I'll give it an ID have to make sure this is the right ID because we're referring to it in our code. Pink switch. And everything else can be kept at default. You see that this pink switch is added under main canvas grid. And main canvas grid is at the same level as main canvas. We want to add a label to the switch so we know what this does. I'll call this pink switch label. And I'll label it Pinkify. Previewing, we'll see that there is a switch on the top left of our main canvas area. Just a recommendation, we want to either keep everything on the sidebar or move everything into overlay. Mixing overlay and sidebar can be very user unfriendly. Could be confusing to see. So I saved this. And if we want to look at how to use the pink switch, we can either select it and click on the documentation, or you can select it, right click, and read documentation. It opens up the same page. GTK switch is a light switch style toggle. The properties are active state functions here. So basically it just controls either it's on or off. The signals, it has two signals. The first one is an activate signal that you should not be using. Should never connect to the signal. And the state set signal is triggered whenever the underlying state is changed. And this is the signal we want to connect to. So in our code, we'll be using this one, this draw map. Everything else is the same, including draw main canvas, including act on mouse click, because we set the GTA grids pass through to be on. So we can keep everything from here. Inside initial setup, we're not adding the Pinkify button anymore. Instead, we are linking Pinkify with the pink switch. So we're first getting the G-object pointer pink switch from the application using the ID that we set in Glade. Where's Glade? This is Glade. ID we set here, pink switch. And we are calling gsignal connect. First parameter is pink switch. Second parameter is the signal. And that's the signal here, state set signal. For each widget you are adding, just make sure you're checking the documentation and choosing the right signal. If you're looking to an incorrect signal, you might get errors. We register a callback function called Pinkify switch here using gcallback passing. And we are passing inside the application pointer. We can either pass in the pointer or we can pass in a null pointer. In this case, because we want to use application, so we're passing in that. The callback function we are registering is here, Pinkify switch. The headers for callback functions you're registering with each widget should be found also inside the documentation. For a switch, it contains GTK switch, ping switch, a Boolean of switch state, and the last one is whatever other pointers you are passing in. So inside this callback function, we are setting the Pinkify flag to the switch state. And we force refresh the drawing so that the Pinkify state shows up immediately and we directly return. But we still remember we still have the text entry, and now we're not reading anything with it. So we are instead registering another signal using gsignal connect with the text entry. So we're the same thing as the switch. We're getting the text entry using its ID. We're doing gsignal connect and we're using activate. Let's go to Blade and see what that is. This is inside inner grid, my text entry, open documentation. Go to all of the signals we have. We see there's the activate, there's the backspace, copy clipboard, cut, delete from cursor. A lot of useful signals there. And activate, what it does is it's emitted when the user hits the enter key. So this callback function will be called whenever the user hits the enter key with the text box. And the text box callback function header looks like this. What it does is it will get the entry inside the text box and directly send it to update message. Very simple. Now let's go to makefile to make and run. We see that the mouse clicks are still working. And there's the Pinkify switch up here to be turned on and off. Pink text is here. If you hit on Pinkify, it doesn't change anything. And if we hit enter, it will show up down here. And if we click on an intersection, it shows the intersection. And if we do enter, it will switch to the text. So that is how to register the signals of our UI widgets with our callback functions. Is everything good? So let me go back to our slides. Just to repeat what we did, we add a GTK overlay, and under overlay, we add main canvas back and the overlay grid. So we're stacking main canvas and the overlay grid together. We set pass through to on in overlay grid, so our mouse clicks are still passing to the canvas. So we don't have to change anything with our mouse clicks. And our final UI looks like this. For the pink text, we can enter to show the text under our screen, and the Pinkify switch controls whether we're Pinkifying the background. and that is overlaid. In our code, to connect callbacks in the initial setup function, we use the gsignal connect. The first one is the gObject pointer that's obtained from our widget ID in Glade. Second one is the signal name to be found inside the log indentation. The registering the callback function, and lastly, the pointer to data you'd like to access in the callback. It's either application or null pointer for not accessing anything. Inside our callback function, the first one is always the pointer to the widget. The second one is the data pointer you set up. And for each different widget, there might be different callback functions with different returns and states parameters. And that's it for the first part. Any questions before I go into the second part? Anyone needs a quick break? Okay, I'll directly enter the second part, which is timing and profiling for performance in C++. So timing and profiling for performance is pretty easily done in our first milestone because we wrote unit tests with measuring performance for all of the functions we wrote. But in milestone 2, it's harder to do because it's a graphical user interface implementation. And to figure out where time goes, your current toolbox contains, firstly, the big O analysis. You can theoretically estimate how long each algorithm takes. And the C++ STL provides the complexity for most of the functions it contains. We can guess based on our ECE244 knowledge, like if we are passing by copies that needs to call the copy constructor is definitely slower than passing by reference. Or we can guess based on what you think you know, which happens to everyone, but it's not a good practice. We would like to actually measure the time to verify our assumptions, like using the stopwatch app on your phone. If you cannot measure it, you cannot improve it. To measure it, we provide you with 3 options. First option, you can manually write code to measure time and you can output them whenever you want. It has the lowest overhead because it can be performed every time you run the program, and you can measure parts of a function that you are interested in. The second option, you can sample using a debugger if you don't know which function to measure. You can open up the debugger. When your program is stuck in execution, click pause, see where you are, continue, then hit pause again and see where you are. This coarsely samples where runtime is spent, and the more you stop in a single function, then the more time is spent in that single function. But this is also restricted because because human reaction is clearly slower than how fast the program runs. So our third option is to use a profiler to measure everything for you. What the profiler does is it will interrupt your program at some sampling rate that's clearly faster than human sampling rate, and it will measure key things during the interrupt. This creates some overhead because it will do a lot of sampling. It will slow down your program. It will generate huge files to visualize. But this works very well for identifying bottlenecks. So we really want you to know. Our first option, which is the simplest, to measure the performance manually by adding some measurements inside your region of interest. What you do is you get the timestamp before the region of interest, get the timestamp after the region of interest, subtract, and you can see the time spent in the region of interest by outputting them in whatever format or units you would like. Say we have this piece of code. We can simply do first get the timestamp before region of interest using chrono high resolution clock. We can save that into start. And after the region of interest, we save the chrono high resolution clock now into end. This chrono high resolution clock now gets the current time inside gets the current time with respect to your current time. So if you then subtract end with start, and you can cast the delta time to whichever unit you like chronoseconds. And then print and record the measurement. In this case, we're printing to the terminal standard output using delta time dot count in seconds. You can further automate it by saving to a file. That's way easier to follow. Like this. At the start of the program, open a file using all offstream output file string called profile CSV file inside act on button press.csv, for example. We're opening up a CSV file for output. Then inside each function that you would like to measure, record the start time, and at the end, call profile CSV with the start time and act on button press, which is the function name. Or you can give any part of the function, any region of a function, the region name for that action. This could be very flexible according to your use. And inside the profile CSV, it gets the start time, it gets the string name. Then inside it, we want to do getting the end time, calculating the elapsed time, and saving it into our off stream. And at the end, we call std end line. So it's flashed directly into the file. The function name and the time is split by commas because it's a comma separated value file format. And std end line flushes the output to file immediately so that even if your program crashed or killed or halted accidentally, it's still saved to the file. And you can see it in action. If you open up the .csv file inside any spreadsheet app, here is what you will see. So whenever it goes over each of your region of interest, it will output the name and the time. In this case, it's in seconds. The act on button press just appeared here. And this is generally how to write profiling, simple profiling code to output duration of each region of interest. And let's see it. So I'll close everything in here. And I'll go to a repo where everything is already implemented. So we have everything implemented in here. And in each of the regions we are doing profiling, profile CSV, on act on button press, on draw all features, draw all intersections, draw all segments, and etc. And for the draw that contains all of those, we are also outputting a draw profiling. I'll go to the make file. I'll run the release configuration. The more you add to your program, the longer it takes to compile. If I run it, so I'll first turn on the subways. I'll zoom in a bit to see enough details. And I'll do a click, do a clear, do a move, close it. Let's see it. In terminal, we see funcperf.csv appearing. I want to open that. I'll first open that in a text editor so you can see it. See that this is a new file that's not in our repo. So it's the function name and the time separated by commas. I'll go to Applications Win Office and open the spreadsheet. The spreadsheet, I'll open the funcperf.csv. Looks like this. Let me increase the font so it's easier to see. So the load map itself took 5.64 seconds. Draw that contains all of the above took 0.216 seconds. And within that 0.216, draw all features is taking on the most time, then draw all segments. Then the other three are actually very small. We have then a lot of we made a lot of moves, we made a lot of zooms, so it's calling draw for a lot of times. Starting from this one, we turn on the draw all subways. We see that drawing all of the subways is not taking much time, so there's no point to optimize for that. And so we see that the time spent in draw decreases as we zoom in until we should see at a certain level we're drawing all of the details, so it slows it down. It's pretty hard to see using this table. In this table, the clearest thing to see is that inside each draw, we are spending most time in draw all features and then draw all segments. The other ones are negligible. Okay, the last draw took 0.348 seconds, and that's because it's starting to show all of the details. And the portion for each one of those staying the same. But there are limitations on this approach because you must know what code to measure. If you don't know what code to measure, you can figure that out using the other two options, which is profiling with random sampling. You can either do it in the debugger by hand. So in this case, we are just by hand running the debugger. We are debugging, pausing, looking at where you are, examining the call stack, and continue, pause, repeat until you see there is a routine that has a higher probability of stopping there. The most time you stop in the same routine means the more time is spent in that routine. The challenge is if you are sampling too slow, it's hard to actually stop fast enough. So what we'll do is we'll write a loop in the redraw function. So in the redraw function, which is the function that we're most interested in, we write a loop to wrap everything inside, and we can make the loop run for multiple times and to redraw many times so that there are more time for you to stop. We can always use the release build. The release build is the most accurate build to represent runtime, but there could be many functions inlined so that your debugger won't stop there. In that case, we can choose the profile build that is turning off function inlining. In this case, the CPU time estimate is still fairly accurate, but it's not as accurate as release. Some functions will seem slower than what they actually are, but it can pause in any function. In our demo, I will only be using the release build. So I'll go to makefile. I have already compiled it. So, but I have to change the number of redraws to something like 30. So we want to redraw 30 times each time we enter the draw function. So I'll compile. And I will debug. If I stop right here, we are inside load map. So we don't want that. We want to continue until the window shows up. And if I'm not fast enough, yes, we are fast enough. We stop in draw feature. I'll continue and we stop in application.run. So the map already finished drawing. I'll continue. I think I clicked on something, so I'll clear path. I'll zoom in and quickly stop. You'll probably click faster than I do. Okay, it's been running really fast, so it's very hard to stop. Stop in draw feature, draw line. Draw feature, fill poly. Draw feature, draw line. Draw feature is closed feature. Draw feature is closed feature. Draw feature, draw line. Draw feature is closed feature. So we're definitely spending most time inside draw feature. Draw feature, draw line. And this is draw feature, draw line. Sometimes we need to scroll down enough to see where we are actually. Draw feature, draw line. Draw feature is closed feature. Draw feature is closed feature. Draw feature is closed feature. So from this, we should be already noticing that its closed feature can be moved out to pre-processing state. Draw feature, fill poly. Draw feature is closed feature. Draw feature is closed feature. Draw feature. Draw feature, draw line. Draw feature, set color, and application.run. So we are always stopping in draw feature. Name again. Draw feature is closed feature. Fill poly, draw feature. Draw feature, fill poly. Draw feature, draw line. Draw feature is closed feature. Draw feature, fill poly. Draw segments. This is the first time we stopped here today, but usually it appears more frequently. Because draw segments is also a big portion of runtime. Okay, we're back to application.run. So that's basically how sampling with debugger works. We will have a somehow accurate sense of where to look at. So now we at least know that we're looking at draw feature most. So the last option, instead of manually doing this inside the debugger, we can use the profile option in the ECE297 exercise script. And then we have the profile visualizer to visualize where time goes. And in this case, we have to compile using the profile configuration, even if it's not accurate enough as released, because somehow the profile won't work correctly. And in NetBeans, it has the profile configuration option. In VS Code, it also has it. Or on command line, we can use make conf equals to profile. Then instead of running the exercise ourselves, we run the exercise with ECE297 exercise, run tester draw Toronto. And this will open up the Toronto map with the profile option enabled. We can open up the map, we can do something with it, and then after we exit, it will generate, the profile option will generate a file called perf.data. And we can use this file to call ECE297 profile visualize to visualize the tree. And in this case, I'll also be adding a loop to the redraw function so that the load map doesn't get dominated. Because we want to focus on the redraw function. So we want to make the time spent in the redraw function more than load map. So I won't change the amount of redraws. This graph will change every time you visualize it. But basically how to look at it is the nodes are the functions, the edges are how the functions are calling each other, and the color scheme represents the time spent, with the dark blue ones, the least time spent, and red is the most. Inside each function, something like draw will call both the draw features and draw all segments. 74.04% is total spent in draw, but 0% self-time. So all of the 74.07% are spent in its helper functions, which are draw features and draw all segments. And for each function, it has the total time spent and its self-time. And draw all features has also its percentages and splits. So it shows 58.23% total time spent are spent in draw all features, and they are called from draw. There's also something called flame graph. We can visualize it using the same perf.data, but with -t flame graph enabled. I personally like flame graphs better than the call graph because it's easier to look at. The width are proportional to the total time spent in each function. And moving up the graph is the function called depth. This will appear in arbitrary order, so it's dependent of the time. It's independent of the time. And if you want to focus on something, you can double click and zoom in. Like if you zoom into draw, you will see that the most time are in draw all features, draw all segments very clearly. And if you focus on draw features, you can see how much time is spent in draw line, how much time in draw fill polys, how much time is in its close feature, and etc. I'll show that in a demo. So I'll have to change the configuration to profile because if we keep it in release, the profile visualizer sometimes it won't be able to find some root nodes, so they'll fail to open. And other times where it fails to open is when the file gets too big. So make sure when you're in the test, just stop right at where you need to stop. Don't flush the file to be too big. I'll wait for this to compile. In the profile configuration, the terminal will start typing in ECE297 exercise 2. Run tester, draw Toronto, -- profile. That's good. Okay. This tester just opens up the Toronto map. And we don't have to measure anything, record anything manually. We can just do zoom in. And because we're doing profiling configuration, because we're doing -- profile, and because we're doing a 30 times redraw, this is much slower than what we would expect. I'll turn on subways, zoom in. And I'll stop as soon as the details are showing up. Should be the next. See that it generated a file called perf.data, and it's not too big, so visualization should work. Do ECE297 profile visualize perf.data? The bigger the file, the longer it takes to visualize it. And that's the overhead we talked about at the first slide. Another option of not letting perf.data getting too big is for your disk quota's sake. You only have 2 GB, if I remember correctly. Okay. So the call graph is showing up. We can zoom in. We see that the most are spent in the EZGL helper functions. In here, there is a call to draw, and it's calling draw all segments and draw all features. And inside draw all features, it's calling draw feature, get feature type, draw feature draw line. And we can see all of the percentages spent. Is close feature. And you can go down or you can stay here. So from here, we can see draw line is taking more than field poly, and it's taking more than its close feature. So there are a lot of things that, and there's the render rectangle off screen. So there are a lot of things that could be pre-processed and not included in our redraws, like its close feature. And sometimes this graph might not show as clear as this one. This one we just got really lucky, and we can actually see it clearly in here for draw features. And there's also the draw of segments, which is not shown in here. And sometimes you might see that some of these, like rectangle off screen, is called by many different functions that I'm not able to show all of them. If you want, you can examine yours, but basically from here, we can see that something like this can be pre-processed, and draw line is taking up a lot. So to see everything more clearly, we can do the flame graph. So it's the same profile visualize tool, the same perf.data file. We just add -t flame graph. And just to repeat, if this command fails, then either you're not using the profile build, or you are having a perf.data that is too large. Wait for it to come up. Okay. So if we look at it, we see load map and close map here. These are all called just once at the startup and closing. And here it has the draw that's led by press zoom in. That's led by some unknown actions. This one is canvas redraw. And this one is press zoom in, G signal emit. So these all three have redraw that's caused by something like press zoom in. And because they have a different call stack, they are appearing at different locations. But if we just zoom in on this largest one, zoom in on redraw, press zoom in, redraw, draw, we see the dominant ones are draw all features and draw all segments. If we zoom in on draw all segments, we see draw segment, and inside draw segment, it has find x from long, and it has a call to cosine. We see that this is taking up a lot of time inside our draw segment. So this is definitely something we can move to pre-processing and just accessing the data physics. There's the draw line, set line width. There are the get intersection position, get street segment curve point, get street segment info. These three chunks are also potential things we can save prior to drawing our map. Let's draw segments. If we then zoom in on draw all features, we have a big chunk that's get feature type. Then inside draw feature, we have a big chunk of draw line and its close feature. So this big is close feature chunk can be definitely moved to pre-processing. And we can just save a Boolean inside the feature struct or something. For draw line, I'll just modify the draw line in this tutorial. So I'll go to draw feature. And inside draw feature, I will make line width equal to 0. Because I know that drawing line width of 2 takes much more time than drawing line width of zeros. So I'll close this one. And this is just to speed up our draw line. I'll compile again with profile. I'll go remove the curve.data. Oh, yeah, passed. Now I'll Go to ECE297 exercise 2, run tester, draw Toronto, -- profile. Wait for draw map to start, and I'll turn on subways as before. I'll zoom in. Zoom in until we're seeing all of the details. Our own names. Getting slow, I'll just stop. But we still have a very large perf data. Wow. So it nearly doubled because of the 2 extra options I made. See if it opens. If this doesn't open, I'll go back to the map and do it again. Oh, it opens. Okay. So this is because I did pan using mouse move. And this is because I pressed zoom in. And if I click on draw feature, we should be seeing that draw line is taking less time. Like this. And this map is definitely not responsive enough. So don't try to match with this map. This map has a lot of things that can be moved to pre-processing, like its close feature, which is taking up this much time. And everything else. So yeah. Any questions so far? Any questions on profiling? So that is the last demo. Any questions? If not, thanks for coming, and that's it for today's tutorial.